All right, so I just got YouTube to start streaming, and what we'll do today is to kind of at least revisit the program that we looked at yesterday, the sample program that we were looking at yesterday, because yesterday I just kind of quickly verified that the program was working, but I didn't really quite go through the analysis of what is going on the stack as we execute the program. So that's kind of what we want to do, or what I want to do today. If anyone has started to write the code, or has started to plan to write the code, but has encountered some conceptual question, today is a really good day to ask, because the assignment is due tomorrow, and that's why today is a good day to get all those questions answered. So I will be keeping an eye on Discord, just so that when people have questions, I can start to answer those questions. And if you're not shy and you want to use um, the voice channel, please go ahead and use the voice channel. It might be slightly more efficient that way, um, instead of using the text channel. But you can use either one. They're both okay with me. All right. So we'll kind of go back to the program that we looked at yesterday. Let me go back to the uh, NVim. All right. So we got the connection timeout. Huh. Oh, that's because I'm no longer using that particular server. Okay, so Martin is reporting a link that doesn't work anymore, and that is correct. Okay, so let me fix that first. And that would be postfix expression in TTP ASM. Alright, so there we go. It's this particular one, and let me fix that first. Yeah, it's not gonna go there because I host my own server. Fortunately, I got the content already backed up, somewhere else. So instead of using a virtual server on Amazon, I'm consolidating everything to the Power server. But sometimes I forget to update the URL, and that's why this one is not working, because it's still pointing to the wrong address. So let me fix this first. https://power.arc.losrios.edu /tilde AUYEUNT, and then tilde again. That should work. So I'm updating it, and we'll give it a try. Yep, looks like it's working now. And I do apologize because I thought I caught every single one of them, and this one I did not catch. So uh, my apologies for having a broken link on the site. All right, so that is taken care of. So with that taken care of, let's go back to the program that we were looking at yesterday. I This is a program that I just thought of using yesterday, because I think this one illustrates a few points. Basically all the points that we have talked about up to this point. It includes, like, what do we do when we have more than one parameters? What do we do when we have local variables? What do we do when we have more than one local variables? And also, what do we do with pointers as arguments? So that's why this program, this particular sample example program is actually particularly useful. So what we'll do today is we'll do an analysis of what is being used on the stack and how it is used in this program. So what we'll do is my computer crashed yesterday, so I lost the spreadsheet. It probably has a backup copy somewhere, but I really doubt it, because if I don't save it, it might actually back it up to a location. Let me give it a try. Start to recover. Yep, it was able to recover the spreadsheet from yesterday. All right, so this is the spreadsheet from yesterday, and what we'll do is we are going to look at the source code, and I'm going to run the program manually, and then we'll try to figure out what we are doing with all the different locations. Okay, so what we'll do is we'll start with main. Okay, so here is main, and also what I'll do is I'm inserting a new row on top of this row here, and I'm going to label that row as 0, 0. Okay, because 0, 0 is technically the 1 byte or the address of the byte that is after the byte at location FF. Because remember, everything is a circle, so that means if I add 1 to FF, it goes back to 0, 0. So from that perspective, 0, 0 is really quote unquote not less than FF, because it is really FF plus 1. Okay, um, so initially the stack pointer points here. Okay, so the D register D is pointing to this location initially, and let me get rid of all this stuff here first. Okay, so that we can actually kind of go through this from scratch. Now when we look at these lines, okay, so let me turn on line numbers. There we go. So when we look at line 68 and 69, those two lines are label definitions. In other words, they do not do a single thing at runtime. They do not generate any opcode. If you look into the RAM file tab, you will see that the two rows corresponding to the label definitions, like these two, there's nothing coming out of the assembler. There's no opcode whatsoever to be loaded into RAM, because labels are really a convenience feature from the perspective of the assembler. And they're really just a way to help us, the programmers, to keep track of values instead of using numerical values, and instead of having us to count the number of bytes and so on. We're just using labels so that the assembler can help us count and help us evaluate and help us remember values instead of remember exact numerical values. Now we can just refer to a name, which makes it a little bit easier. So that's why there's nothing happening on the stack on because of line 68 and 69, and the same thing applies to line 70, because line 70 is really just a way to tell us, okay, so if we add up all the bytes of all the local variables, how many bytes do we use? Now the reason why we use line 70 is because we want to now use line 72 and line 73 to allocate for all the local variables. So that means if main doesn't need any local variables, we can simply define main local var size to be 0. Now, if the label main local var size is 0, then line 72 and line 73 really literally does not do a single thing, because register A would get a 0, and then subtracting 0 from D means D does not get changed at all. But it is a universal approach, so if you don't want to make a special case for subroutines that do not have local variables, and subroutines that only have 1 byte of local variable and you can use a decrement, and subroutines that use more than 1 byte as local variables where you want to do the actual subtraction. If you don't want to make any special cases, this is the quote-unquote universal way to allocate for local variables. Even when there are no local variables, it is still not wrong to do it this way. Okay, it does waste a few cycles in terms of execution, but at this point, as far as we are concerned, the concept is far more important than efficiency. So it's okay to keep line 72 and line 73 even for subroutines that do not use any local variables. Now, if you remember how I did this program yesterday, as soon as I typed in line 72 and line 73, I immediately type in all the way back here. So I automatically type in line 99 and line 100. In other words, if I allocate, I immediately do the code to deallocate. This way, I do not forget to do it later on. Okay, because it's just like when you type an expression and you use parentheses. The way I do it is, as soon as I type an open parenthesis, I type the close parenthesis right away, and then I go back to fill in whatever is supposed to be within that pair of parentheses. If you have used some programmer editor, you will find that many of those will do it with braces. If you type open brace and then press the enter key, it will automatically insert the close brace for you. So this way, we don't forget to do it later on. So this is really just a programming practice. It's just the way I do it. Okay. Now these two lines actually do something to the stack, or at least the stack pointer. So line 72 is loading A with a value of 2. Line 73 is subtracting that 2 from D. Oops, I just pressed the wrong key on the mouse. So now register D is 2 less than what it used to be. And if you subtract 2 from 0, 0, it actually gets to FE. So register D is no longer pointing at this location, and it is now pointing to this location when we get to line, after we execute line 73. All right, are we doing okay so far with what is being done on the stack? Okay, I'm not seeing any questions. Okay, now that the register D or the stack pointer has changed to change, it has changed to point to the location FE. We can now start to label which one is I and which one is J. So the way, the convention that I define these labels is they are offset from where the stack pointer is pointing to. So by defining J to be 0, that means I need main J to be here. So local variable J of main is at 0 byte from where the stack pointer points to when I am in main. And as a result of that, main I is going to be here because main I is Ji1 plus, is J1 plus, which is 0, 1 plus. So that means it is just 1. So label I is 1, which basically means it is at an offset of 1 byte from where the stack pointer points to. So right here, okay, if you want to label these 2 bytes, okay, these 2 bytes is the frame of main. Okay, it's only the local variables. There's no return address because main is not called from someone else. There are no parameters because in this particular architecture, main is not called from a caller, and as a result, there are no parameters for this main. And one really useful feature you can use is to merge cells, and then you can now say this is the frame of main. Okay, I would say main frame, but it really means the frame of main. Okay. All right, so getting on to this code here. The next thing we do is line 77, and what line? Whoops, I take it back. Line 75 and line 76 is computing the address of I. So if I want to use the same spreadsheet to illustrate what that really is doing, okay. So by the time I'm done with line 76, register A is pointing to local variable I. So basically, you're looking at something like this. Okay, so register A is pointing to where I is, and then we load 7 into B, and then we store B into whatever A is pointing to. So what that is doing is it is initializing that location with a particular value. So at that point, okay, if I use column F to represent the value of a particular location, so at that point, okay, I can shrink the columns a little bit because I don't need them to be this wide. So give me a second here to format the spreadsheet a little bit. There we go. So now we can fit everything, and still have everything to be viewable. So column F is representing the value, whereas column A is representing the address. So by the time we are done with line 78, we would have stored a 07, or just 7, into location FF. When we get to line 80, 81, okay, by the time we get to line, when we're done with line 81, it's the same thing. You can see how line 75, line 76 are really the same thing as line 71, and 81 and 82. So register A will once again be pointing to variable I of main. But this time what we do is we I just repeated the code? No. So this time I retrieve the value that A is pointing to into register B. So in the trace analyzer, you will see that variable B is 7. But you actually won't see the update because it was 7 already at this point. So I'm basically just reloading 7 back into register B. So it doesn't really show on in the trace analyzer because register B has not really changed its value, even though it's an update operation, but it's updating it to exactly the same value. On line 83, we decrement register D. So register D is now pointing to one location below where it was pointing to before. And then on line 84, we store register B to whatever D is pointing to. So that means this location, which is FD, is also going to get the value of 7 at this point. If I want to give it a name, this is our parameter V of the subroutine. So I'm going to say this is the subroutine F's parameter V. And then after that, okay, we got some questions. What is the purpose of the code for line 80 to 82? We are okay. So the assumption that I was making yesterday is we do not make assumptions about the content of registers across statements in C. So if we switch back to the C code here, we can see how the initialization of I is one statement. Okay, we know it's a statement because of the semicolon. And as a result, this is a whole different statement. So even though I got the values of the address of I and also the value, which is 7 in register B because of the first statement, I'm not making that assumption because we're working across statements. Now, if you want to optimize, obviously you can optimize it quite a bit. In other words, if you really want to optimize the code, this line is not needed. This line is, well, these two lines together are not needed, and neither is this line over here. In other words, line 80 to 82 can actually be commented out, and the program will still work exactly the same as it did. But I'm not making the assumption because I don't want people to have to memorize or have to keep track of which register already has what value that we can reuse. So I'm just starting from scratch when we start on this line in C. Okay, I see. Okay. Yeah, so that's why it is duplicated. It's only because that I don't want to make assumptions that certain registers already have certain values when we get across to a new statement. If people want to do that, that's okay. Okay, if you want to, when you're writing your program for the lab or when you're writing programs for the final assessment, I still haven't decided yet whether it's going to be just a project where you have more time or whether it's going to be an exam kind of in the same format as the first and the second exam. I still haven't decided yet. But if you need to write code for the final assessment, you can optimize or you can not optimize, so either way is fine. I'm just looking for correctness. I'm not looking for efficiency. All right, so getting back to the spreadsheet, because the spreadsheet is really helpful. This is something that you can potentially do with your own program for the lab, okay, because it's good to understand what is going on the stack, what location is actually doing what, is fulfilling what role in the original C program. So we are trying to map between the C code and the assembly code. All right, so now we have a decrement D again because we are allocating another byte. So register D is now changed to point to location FC. We are talking about line 83 here. And then on line 84, we are storing B into that location. Nope, we did that already. So we decrement D one more time. So this decrement over here, going from FD to FC, is actually corresponding to line 85. So I apologize for that confusion. So the current location that D is pointing to corresponds to right after line 85. It is pointing to the location where px as a parameter is supposed to be in on the stack. So this is the px parameter of f, and D is pointing to that location right now. And what we are storing into that location is not B. Register B has the value of local variable I of main, but register A has the address of variable I of main. And that is what we are storing into this location. So depending on how you want to document this, you can say this is FF, because that is where A is still pointing to at this point. So A is still pointing to local variable I of main, which is at location FF. So you can write down FF here if you really want to track the literal value on the stack. But symbolically, we are really storing the address of I of main. That's basically what this FF is about. Okay. All right. So then we have main return. Okay, main return point 0, put into register A. So at that point, register A is no longer pointing to FF. It has main underscore return 0 as a label to continue execution. Then we decrement D again, and then we push this return label into this location. So that means the stack pointer is moved again, and this time it's basically the return address back to main. So I'm just going to use an abbreviation here. So location FB actually now contains the main's return address, the return address where we need to go back to in main. And then we do a JMP-I to label F. So now we continue execution at label F, at the very, very beginning of F. There we go. All right, so F has a whole bunch of comments. Okay, obviously they don't do a single thing. And then we have a bunch of label definitions. We have the label T, the label F underscore local var size, the label PX, and the label V. So remember, label definitions do not change anything at runtime because they do not generate any actual opcode. They're only defining some symbolic terms so that we, the programmers, can refer to those symbolic terms. So the first line that actually does something is line 24. Line 24 is loading F underscore local var size into register A, and that is just 1, okay, because T 1 plus is just 1 because T is defined to be 0, and then we subtract that register A, which is a value of 1 from the stack pointer. So the stack pointer decrements again. There we go. And this time, where it is now pointing to, what the stack pointer is now pointing to, is local variable T of F. So this is the local variable T of F, because at this point, okay, after line 25 executes, then we have the frame of local variable, we have the frame of function F defined. So if you want to label what is the frame, then these 4 cells, these 4 rows, I should say, these 4 rows, they all correspond to a frame of F. So it's a F frame right there, okay? So do we have any questions about how I am visualizing how the stack is being used? And this is all done without using the trace analyzer because we are just manually tracking everything. So are we still good at this point? I'm not seeing any questions. I think this part may be the biggest transition for me is in a face-to-face class, people have no choice but to actually ask questions or nod. But when I do this class online, I have to kind of read the text, to find out, what is going on. Okay, line 18 to 22. So line 18 to line 22 are label definitions. So the label definitions are each label is representing an offset. It's an okay, except for one, except for f underscore local var size. So t, px, and v, they are all basically offsets. The positioning of each one, sure. So we can see how the stack pointer is now currently pointing to location fa, which we are using as local variable t of f. So that means the offset of local variable t from where the stack point is pointing to, as far as this frame is concerned, is 0. And that's why t as a label is defined to be 0. F underscore var size is defined to be t1 plus because t is the offset to the last local variable, or the local variable that has the highest address. And then the 1 plus is basically because local variable t has a size of 1 byte. So when you add the size of t to the offset to t, because t is the local variable that has the highest address, then you get the size of all the local variables added together. So that's how we define your f underscore local var size. And then 1 byte above all the local variables is the return address. So that's why px as our first parameter is 1 byte beyond that. And that's why px is, as a label, is defined to be f local var size 1 plus, which basically translates to 2. So when you look at this, this is d plus 0, this is d plus 1, this is d plus 2. So px as a parameter of function f is 2 bytes past where the stack point is pointing to, and that's why px is literally defined to, well, not literally, but it is defined to be 2. Yeah, you can look at it that way. So f underscore local var size is the same as where the offset to the return address. That is correct. And then v is just 1 byte past px because we push the parameters in reverse order. The first parameter is pushed first. Whatever is pushed first has a higher address, and that's why px has a lower address and v has a higher address. And v is now defined as px1 plus, which is 1 byte past where px is. But all of these labels are defining offsets from where the stack pointer is pointing to. So are we good so far? Shall we proceed? Okay. No, we do not want to use negative offsets because anything below where the stack pointer points to is not guaranteed to be there all the time. Okay, because if you try to access anything that is below where the stack pointer points to, I haven't really talked about interrupts at this point, but when interrupts happen, okay, so the bottom line is there's no guarantee that the content of memory below where the stack pointer points to is going to stay the way they are. Okay, things can come in and do things to the locations below where the stack pointer points to. So whatever you want to use, you make sure that it is either at or above where the stack pointer points to. Correct. So it is considered deallocated, which means it is free for other things to use those locations. And one of those things is an ISR, or an interrupt surface routine, but we haven't really talked about ISRs yet. Okay, so that's a topic that we can talk about later. But at this point, I think it is important to just remember that you do not want to make use of any location that is below where the stack point points to. All right. So if assuming there are no questions about the label definitions, so when we get to line 24 and line 25, we are allocating for the local variable, so that's why D is now pointing to FA, which is our local variable T. And then when we get to line 27 and 28, we are computing the address of PX and make A point to PX. So that means A is now pointing to PX. So if I want to document it like this, that's basically what is happening at the end of after we are done with line 28. And so I shouldn't have used my mouse pointer. So when we get to line 30 and 31, this is where things get kind of interesting, because when we right after line 30, okay, right after we execute line 30, register A is no longer pointing to this location, because register A will then have a value of FF. So register A is now going to point to this location. That's right after line 30. And right after line 31, register A will no longer be a pointer, because it actually now has the value of local variable I of main. Okay, so at that point we just kind of go like, okay, so A is no longer actually pointing to any location right after line 31, because A simply has a value of 7, because it has the content of location FF. Yep, sure. How about this? We can actually switch to the trace analyzer. Okay, so I'm going to switch gear a little bit here, and we'll start to use the trace analyzer for this part. Okay, so the trace analyzer is here, and to use the trace analyzer effectively, it is good to make use of the assembler as well. So we get back to the assembler, and I did one little modification to the assemble tab. I hid the columns that are not really useful to us, so they are no longer showing. So we skip from column A all the way to column U. So now we go to function F, and which row are we talking about? Okay, row 30 and 31. Okay, so we are looking at this instruction here, and it's still doing something. It's still loading the content. And it doesn't look like it's gonna get it done. Okay, let's do a refresh. There we go. All right, so we are now at on line 30, and the row number corresponds to the line number as long as you don't make any changes. This is at location 09. Column W is the location in hexadecimal, is at location 09. So when we go to the trace analyzer, we want to execute at 09. So it is right here. So at this point, what is happening is register A is FC, and at location 09, we have a LDAA instruction. So the assembler can show that we have a LDAA instruction. So what it's doing is it's dereferencing register A, which has FC in it, and it's going to that location and retrieve the content at that location. Location FC has a value of FF, and is putting that value FF back into A. That's what this LDAA, the first LDAA, is doing. So in the trace analyzer, we can clearly see that register A went from FC before this opcode instruction to FF after this opcode. But at the same time, if we go back to our kind of ad hoc, stack visualization, we can also see how location FC is actually our parameter PX, but the parameter PX is a pointer. It is pointing to location FF. So what the instruction at location 09 is doing is A is pointing to FC initially. We retrieve the content, and then we put that content FF back into register A. So that's what happened when we execute LDAA, the first one, at location 09. So does that answer the question? Does that work? Okay, cool. So now we can move on to the next one, which is another LDAA instruction. It is at location 0A. So this time we use register A as a pointer first. Okay, we let it point to location FF in RAM. But when we look at the visualization, we know that location FF in RAM has a content of 7. So it's retrieving the value of 7 from location FF in RAM and storing that into register A again. And that's why we also see at the end of this operation, register A is now updated to 07. And that's after the second LDAA instruction. Now, if we go back to the actual source code, what we have done up to line 31 here, between line 27 and line 31, okay, inclusively, all that does is to do this one little thing in C. We're simply dereferencing PX. We're finding out what value is pointed to by the pointer PX. And that's indicated by the comment over here as well. So are we good so far? All right. Then the next thing we do is we use register B because register A is in use. So what does star 07 equal to 03 do in the trace? Okay. So in the trace, you're referring to column B. So what column B does is it's basically reporting potential read operations of RAM. So as a side effect, okay, it is reading location 07, which has a content of 02. But that's really useless to us, okay? It's quote unquote reading that location because after we change register A to 07, RAM is still selected and it is still in LD is still a 1, so we are still reading RAM. But since register A has changed from FF to 07, so we are now, instead of reading location FF, which has a value of 07, now we are reading location 07, which has a value of 02, but it really is a side effect that we don't need to pay attention to. That is correct. We are not doing anything with that 02. It is simply an artifact that shows up in the trace analyzer. How do we know when to use LD versus LDI? Well, okay, so let's see how they are different. Okay, so if I want to go into nag mode, okay, which I try to avoid, but if I want to get into nag mode, the nag mode is basically saying, well, maybe you guys can do a control T by control D, transition by transition test of what those two instructions do, okay? And then go to the opcode table and find out how they are different. LDI, there's an I in the LDI. So the first question is, what is that I representing? Now, I have explained that in class already. So I'm waiting for you guys to help me answer that question. It's a constant, exactly. Yep. So LD is loading. Where LD gets the content to change a register depends on yet another register, okay? It could be another register, it could be the same register, but basically it's using a register to specify where in RAM to read a value to update a register. That's what LD does. LDI is simply saying, well, whatever is after the opcode is the constant that I want to put into a register. So LDI can only load a constant. That constant technically cannot change while the program is running. Okay. LD, on the other hand, is loading. Well, it's not loading from a register. It's loading from where a register is pointing to. So that is the key, because otherwise, if LD loads from a register, then that makes LD the same as a CPR, which is copy register. So those are the three instructions that you guys kind of have to differentiate. And I can explain it, okay? Obviously, I can explain the whole thing, but I don't want to. But Tech, you're the professor. You're supposed to teach us. Yes, I'm supposed to teach you guys how to think and how to figure things out on your own. So I'm going to give you guys the tool, and you have to use that tool to work on this to understand it. Okay, but I can give you an idea. I can give you the dots, but you guys eventually have to make the connections. Okay. LD versus ST is a little bit easier because one is a read and the other one is a write. Whatever is in parentheses is a dereference. So let me just kind of use use mouse pad here as my quick whiteboard. Okay, so I want you guys to look into LD versus LDI versus CPR. Okay, look into these three instructions. First place to go is the opcode table. Okay, go to the opcode table, find out how they are documented. Second thing, okay, is to make a tiny program. Okay, now you can do this in GUI mode, and in fact, I would recommend that you do it in GUI mode. So write a simple program, okay, something like LDAB. Compare that to CPRAB, okay, and see what happens. Okay, so what you want to do is to do a control T, do 4 control T's until you get to the actual instruction. So your actual program is going to look like LDAB and a halt instruction. But before you run the program, you might want to load special things into register A and register B, because otherwise they're all going to be zeros and it's not going to be very interesting. So you might want to put something into register A and put something into register B, and based on how you understand the opcode table, put something into the location that register B is pointing to, and then control T 4 times, to get past the fetch and decode steps of executing instruction. So by the time you get to the actual ROM slice, okay, the microcode slice corresponding to LDAB, analyze the processor. Okay, and I have done that multiple times already, so I want you guys to do it this time. Okay, so analyze the processor, figure out all the multiplexers and demultiplexers, which registers enabled to be updated, and so on and so forth. Okay, then you will understand what LDAB is really doing. Then you do the same thing to CPRAB. Okay, figure out what pathways are established between the registers. Is RAM involved in this case? I don't know. Maybe. Okay, you need to figure it out. Is the ALU involved in this step? I don't know. Maybe. You have to figure it out. So then you want to do another one, which is LDIA with a particular constant. Let's say 78. Okay, this 78 is actually in decimal. It doesn't really matter. Pick a random value or whatever. Okay, do a halt instruction here and do exactly the same thing. Okay, start from the beginning of the program, control T 4 times, and then use that slice in the microcode to figure out what is actually being done in the processor. Okay, so I highly recommend that you guys do this. If you have questions about what what are the differences between LD, CPR, and LDI, do these experiments and use the basically the processor is open sourced. Everything is out in the open. In other words, you can track down how things are connected between the components. And when you see how things are connected differently between an LD versus a CPR versus an LDI, that is when you really start to understand how these instructions are different. Now we can throw this into the mix, okay? We can throw ST into the mix, but ST and LD are really kind of the same thing, except the direction is different. One is reading from where a register is pointing to. The other one is overwriting where a register is pointing to. Okay, so they're only opposite in terms of direction, but otherwise they're about the same. So So I will leave this matter as I just talked about. Um, if you have done your experiment and you don't understand one particular aspect of how the processor is configured, then ask me questions about that. Okay, take a screenshot about in that particular time, in that particular slice, in that particular instant of time. Then you can ask me a question about, okay, but I'm not really quite sure what whether this thing is connected to that thing or not. Okay, you should be able to answer all the questions, assuming you know how a multiplexer, a demultiplexer work, and how registers work. But that's kind of the topics that we have already talked about a long time ago. So are we good so far? Can I turn off my nag mode now? Okay, I'm going to assume that I can turn off nag mode for the time being. But seriously, this is much better than me telling you the answer, because if I just tell you the answer, you're gonna forget it. But if you try to figure it out by yourself, then you're gonna remember it. This is also why the processor is done the way it is. I could have just written a simulator program without using Logisim, but the idea of using Logisim is to make everything visual so that you can follow how the processor works by just looking at the multiplexers and demultiplexers, so that you can actually figure out what components are connected in the execution of which instruction. So that really is important. All right, so getting back to here, so we are now ready to execute the instruction at location 0B. So at 0B, okay, my tab just went to sleep. Maybe I should make it not go to sleep. So let me keep this tab so it doesn't sleep. There we go. Because otherwise we have to go back and forth all the time. Okay, so the next instruction is guess what? LDI. Okay, so something that we just talked about. So LDI is loading the second operand, which is the label V, to register B. And you can actually see from the code that it is emitting that V is basically just 03. So it's basically putting 03 into register B, and the location is 0B itself, 03 and 0B, sorry. And if you go back to the trace analyzer, you will see that. Okay, because when we execute the instruction at location 0B, register B is updated to the value of 03. So now the question is, why do we do that? What is the purpose of doing that? The purpose of doing that is really just to set up so the register B eventually will become the address of V, and then it becomes the value of B. So if you look at line 34 and line 35, right after LDI BV, that is what we are attempting to do. So if you look at these three lines as a whole, line 33, 34, and 35, they are really just putting the value of V, the parameter, into register B. So if we go back to the trace, okay, and just kind of fast forward a little bit, we can see how register B did get parameter V, okay, because we know parameter V is 07. How do we know that? Because when we look at the analysis of the stack, we can see that parameter V, which is this one here, at location FD, has a value of 7. So are we still doing okay so far? Because I'm just executing the program step by step without using well, okay, I did use I am using the trace analyzer, but this is all done manually. So are we still doing okay with the execution of the program? All right, so this is good. Okay, great. And then we add the 2, because at this point, register B basically has this part, register A basically has this part, and the right hand side of this assignment is the sum of the 2. So that's why we have an add instruction on line 37, is to compute the actual value of the entire right hand side. So it's basically just 7 plus 7, because px is pointing to local variable I of main, which at this point has a value of 7. V is a parameter that main passed to f, but v also has a value of 7. So 7 plus 7 is 14, which is 0e in hexadecimal. So after the add instruction, we should see 0e in register A. So if we go back to the trace analyzer, we can see that, oh, that really is the case. Okay, we see some of the flags got changed because these flags were earlier changed because of some subtraction instructions, and now they're changed back to 0, and that's why it is reflected in column E. Okay. So now that we have the right hand side, we have to do something about the left hand side. So after we are done with the right hand side, which now has the value stored in register A, register B is free again. So when we look at line 39, line 40, and 41, excuse me, I take it back. If we just look at line 39 and line 40, they are just computing the address of local variable t. By loading the offset into register B first, and then we add the stack pointer to the offset. So that becomes the actual address of local variable t. So let's go back to our stack diagram. Local variable t is here, and label t itself is a 0. So 0 plus the stack pointer is just the stack pointer itself. So register B basically points to exactly the same location at that point. So the trace analyzer should tell us that, should confirm that. Register B should have the content of FA at this point. So let's double check that. So we go back to the trace analyzer, just scroll down a little bit, and we do in fact see that register B is FA, and FA, according to our stack analysis, is the address of local variable t of function f, of this particular invocation of function f. I should be much more specific than that. All right. And then the next instruction in the program is an st instruction, because we don't want to read local variable t. It is not even initialized. So this is the initialization of local variable t. So we want to overwrite location, the location corresponding to local variable t, and update it to 0e. So when we look into the trace analyzer, this is the update. So, and it's done by location 13, okay, the instruction at location 13, which is our st instruction. So when you go to the assembler and you go to the location, what was it again? st is at location 13. It is a store instruction. It is using register A to update the location in RAM that register B is pointing to. And the trace analyzer is confirming that that really is the case, because register A is pointing to register B is pointing to location FA, and then register A has the value of 0E. So it is now updating the value, it's updating the value of location FA in RAM to 0E. So are we still doing okay so far into this trace? Okay, very good. All right, so let's go back to the program. Well, that really is kind of, the next line is not much different. Okay, if you look into the C code, okay, the next line is really not that much different, except we're updating whatever px is pointing to, but the concept is really the same. If you understand line 7, how line 7 in the C code is translated into assembly, then you already know how line 8 should go, because line 8 is a little bit different in the sense that whatever we're updating is not a local variable nor a parameter. It is where the parameter itself is pointing to. But that really is kind of a small twist into this whole thing. Are we understanding how to utilize the tools to kind of develop and also debug a program like this. All right. So when you're writing a program like this, okay, I think so. Okay, that's good to know. So when you're writing a program like this, my recommendation is don't go too far without testing your program. Okay, my recommendation is don't write any more than 5 lines of code without first testing whether those 5 lines of code is correct or not. Now, label definitions does not count. Okay, so I'm only referring to um, instructions. Okay, mnemonic lines. And the first thing that you might want to do is simply to stop right at the entry point of the subroutine. In other words, the first thing you do is to do something like this. Put a halt here. Because then you can understand, you can do this in GUI mode using the processor simulator. Because when we get to this halt instruction, then you can see what D is, okay, what the stack pointer is and where it's pointing to, and then go into the RAM content and find out what exactly is the content and try to explain what you're looking at. Okay, once you understand what you're looking at and you can identify that what the parameters are and what they mean, then you can proceed to write some code and maybe just to allocate the local variable, and I mean, you can proceed, a little bit further along. Okay, so if you look into the swap subroutine, it looks a little bit like this, right? Because you have a dereference on the right hand side and local variable t on the other side. So that means you can actually borrow some of the code that I have written here in your program. Okay, but don't just copy and paste. Okay, you just try to understand what is going on in this code first. Once you have understood, then you can actually recreate the code itself. Okay, or you can copy and paste. I don't care, but the idea is you want to understand this code first. Do we have any questions? So I'm gonna wait a little bit for people to either confirm that there are no questions at this point, or to start to ask questions, because we're good. Okay, what about the rest of the class? Does anyone have any questions at this point? Okay, cannot think of any at this point. Okay, I can understand that. That's what I hear. It's difficult to know what to ask. This is basically an X-ray vision of a C program, because all of this stuff is happening underneath C code. So whenever you write C code, this is actually what is happening underneath. Now the instruction set is different, when you use different processor architectures, but they're basically doing about the same thing. All right. All right. So I'm not seeing any questions or anything specific. So what I'll do is I'm gonna shift gear just a little bit. Because I want to talk about revision control, because when you write programs like this, because you'll be writing a small number of lines, and then you debug it, and then you write some more lines of code, it would be a good idea to have some kind of revision control system, so that you can find out what you have changed between certain revisions. So there are tools to do this. Okay, so this part is not specific to assembly language programming. It is applicable to all forms of programming. So what I want to do is really just to present a few options for you guys. One option is obviously GitHub. Okay, so GitHub is a web resource, but it's also a resource they can access using command line tools. It's for revision control. It's also for collaboration and stuff like that. It's an overkill for what we're doing in this class. But if you have time to learn, GitHub is not a bad idea. Okay, it's a good tool to learn how to use. A lot of employers would value people who know how to use GitHub. So what if you don't want to use GitHub because that takes quite a bit of time to kind of understand the concepts? You can probably find quick tutorials on GitHub or on YouTube. There are many people who have developed a lot of tutorials for GitHub. It's basically a tool so that you can do collaboration. So let's just say that we have a project. It's divided into 4 pieces, and 4 developers are basically working on the project at the same time. What GitHub allows people to do is you can keep your dirty, unfinished, unpolished, and unchecked code to yourself. When it is time, so let's say another team member says, okay, I'm done with my part, I got an update. So you can incorporate an update from somebody else into the code base that you are working with. So this way you can incorporate new features, new APIs and whatnot, because somebody else has done that work already and they're ready to release the code. So when you're working on your own code, you can do revision control. So every time you make a change, you can check in to the repository and say, okay, I have made a change, but you're not releasing it yet. Okay, so those changes are only visible to you. The rest of the team cannot see your intermediate changes until you you commit the change into the repository and just say that, yeah, I think this is ready for releasing and I want everybody else to update to this version of my code, then people can do it that way. So you can kind of see how this can get complicated. GitHub actually supports people working on the same file. Okay, so you can basically have 4 people working on the same file as long as they are not making conflicting changes, like one person deletes a line and the other one, well, they're making conflicting changes to the same line. As long as that doesn't happen, GitHub can resolve all the changes. So it's a really cool useful tool to learn, but it is not really applicable in a class setting because you guys are supposed to be working on your own program, not working on a single program together. All right, good job, Martin. You can even go to YouTube. Okay, if you go to YouTube and just look for GitHub or Git tutorial, you'll find plenty. But apparently Martin already knows this one, so so that's good to know. Okay, but as I said a little bit earlier, it's an overkill. Okay, this is really an overkill for what we are doing in this class. So the other thing you can do, okay, let me. I think I can just start it from here. Another thing you can do is really, it's funny, but it's not funny. You can go to New and then use Google Document, because Google Document actually track changes. So, and you can basically copy and paste program into here. So let me illustrate what I mean by that. So let me switch back to my editor over here, and I'm going to do the same thing that I did before, which is cat pe.ttpsm to xclip cell clip. So now the program is in the clipboard. I switch back to the browser and I do a Control V. Oh, this is ugly. It doesn't like it. It's combining all the lines into one single line. That is not what I want to do. So I might have to get out of NVim and use mousepad instead. So let's see if this is better. So mousepad clearly knows about the lines. Control C, and I go back to here. Control V. There we go. Much better. So what you can do is now you look at this code, and you do some development. Okay, so let's just say that I put in a whole bunch of useless instructions here. Okay, so no up. And at some point I do something, let's say, pretty stupid. Okay, so I forgot to do this line over here, or I erase it, or do something that I'm not supposed to. Okay, maybe I put a halt instruction here, and then I forgot that I have put a halt instruction here, wondering why is this program halting at the wrong place. Okay, Google Document has revision control built into it. So let's give this program a label. Okay, we'll call this PE. Okay, and what you can do is you can type Control Shift Alt H on the keyboard if you're using Windows. I think on a Mac it is about the same. So what it does is it brings up the revision history of the file. And when you see this symbol, it means you can do a drop down. Okay, so here's a drop down. And now you can see all the changes. Okay, so you can see all the individual changes, how I inserted no op at this particular time, and then before that I pasted in the entire program, and so on. Okay, so you have a form of revision control just by using Google Doc, and you can copy from Google Doc to the assembler. Okay, that works. It's not a problem. So this is a very crude way for you guys to do revision control. It is not so crude if you actually utilize labels. So you can actually name versions. So you can name this version as the initial version. Okay, this is the initial version of text code. So now instead of looking at just the date and the time, it now has a name. So as you continue to make more changes, okay, if you test your program, it is getting past a certain point, then you can label that version using another name. Then you can control click different versions, or I thought you can do that, to basically look at all the changes since a particular revision. So this is a really good tool. It is already available because all of you have Google Document access through apps.losrios.edu. So this is one kind of interesting way for you guys to work on your program so that you can have some degree of revision control. It's also good from the perspective of if you want me to take a look at your code, you can now just share this code with me. Then I can see your entire program. So that makes it easier for me to kind of pinpoint issues, or to comment and basically say, okay, what do you think this line is doing over here? Okay, so I can make suggestions like that. So just a tool, suggestion, instead of using a Notepad or Notepad++, use Google Doc because it has built-in revision control. All right, so do we have any questions up to this point? Just kind of working on the tools. No questions. All right. So I'm basically done with explaining this particular program. The PE program is pretty much done. And as I was saying a little bit earlier, it would be useful to kind of go through test programs so that you can understand how the LD, CPR, LDI, and ST instructions work. And I think that is actually really crucial at this point of time, that you understand how these instructions work. So that's something that you might want to work on. And if there are no further questions, what I want to do is to illustrate with another program. So are we ready for that, or do you guys have any specific question on the material that we have introduced up to this point? How do you tell what is changed in the next version? And I'm guessing that is referring to Google Doc. Okay, so let's go back to the Google Doc. All right, so where is the one that I just worked on? Right here. There we go. All right, so you can go to File, go to Version History, and see Version History. You basically have to kind of click on these boxes, but if there's a drop-down box, you can actually just use the cursor key to go from one to the other one. So that's how you can look at the changes will be highlighted in this kind of format. Yep, it highlights changes each time, and I'm not sure whether you can compare two very specific versions, because control click doesn't work, shift click does not work. So I'm not 100% sure if you have a very specific version that you have to you want to compare to the current one. Basically, when you click on each revision, it tells you how it is changed from the previous one. Now, if you use only show named versions, then potentially you can do it, because now it doesn't show all the intermediate updates, so you'll be comparing only the named versions, which is very helpful because you don't want to track every single new line that you add, every single little editing that you do. So if you want to compare just the named versions, this may be the option that you want to use for that. So are we good so far? All right. Okay. So if you have any questions about the program that we talked about today and yesterday, we can talk about it. But unless somebody has a question about that, we're going to look at another program, okay? And it illustrates a slightly different aspect of calling subroutines. So I call this nested call, okay? We'll work on the C code, and maybe we'll have time to work on the assembly code today. Maybe we'll have to do it tomorrow. But this is not needed for your lab, okay? So this goes a little bit beyond what we are doing with the lab. So what we'll do is int8_t, and this one is a little bit easier, okay? If you look at the function add, all it does is to add a and b and use that as my return value. Okay, so this is a whole lot easier compared to PE, because we are not using any dereferencing of the parameters themselves. We're just saying, okay, get me parameter A, get me parameter B, give me the sum. That becomes the return value. So the subroutine for add is pretty easy to understand. But the way it's used in main is where it is a little bit challenging. Okay, so what we'll do is we're going to call add, and you don't have to use the return value. Okay, you can just kind of call a subroutine that returns a value, but totally ignore the return value. So that's perfectly okay syntax-wise. It is not okay from the perspective of, but doesn't that make this program totally useless? Yeah, it kind of makes it useless. So we'll have 3, 7 on one side, and then we'll have, I don't know, 5 and 17 on the other side. Okay. This program will compile. Well, once I pound include stdint.h, the program is going to compile. It doesn't do anything particularly useful, but we know the return value of the outer add invocation should be adding 10 and 22, so it should return a 32. So now the question is, how does that translate into assembly code? So we'll switch to the assembly code side and figure it out. So we have jmpi to main, then I can write the subroutine add over here. So as usual, I want to have symbolic names for my parameters. So in this case, I have no local variables. So if you want to do things in a very, very systematic way, you can always say add local var size is 0. We do not have any local variables. Okay. Then return address is always 1 plus that, and then our first parameter A is always going to be add local var size 1 plus, and then B is A 1 plus. So somebody is going to have a question in his or her mind right away. It's like, we have registers called A and B. Is it really okay to use A and B as label names? The answer is actually yes. Okay, you can, if you want to, use you can use A, B, C, D as labels as well as register names. The reason why that works is because registers cannot be used in a context where a label is expected, and vice versa. So by context, the assembler actually understands which one you're talking about. Okay, let me show you what I mean by that. If you use LDAA in this context, it is not a problem. The assembler will gladly assemble this instruction, because in this case, the B is not referring to a register. It is referring to label B, which is an immediate constant. It's perfectly okay. On the other hand, if you use LDAB like this, then the assembler automatically understands that the B in LDAB is referring to register B, because you cannot use a label within the parentheses. That is just not allowed. The opcode table already puts the constraints on all of this stuff here. So that's why we can actually use A and B as labels, even though they are names of the registers already. Okay. So, but if you want to avoid confusion, okay, we can do something to avoid the confusion. So if you want to avoid the confusion, we can always rename these things as XY and then change this to X and that to Y. And we'll make corresponding changes over here, and everything is good. But I do want to point out that labels A and B are fine. They're not problems. They're just kind of confusing to look at. All right, so we'll go ahead and get through this add subroutine quickly, because that's actually the easier part. But first, I will answer some questions. So Kyo is typing. So is that postfix notation right? I'm guessing that you are referring to line 6 and line 7. Which line are we referring to? Both? I think they're fine, because they are postfix notations. We specify what values we want to work on, and then we specify what to do with those things. Remind me again where the return address is. The return address is right before X. In other words, add local var size can be used as the offset to the return address, because what the stack looks like at this point is Y being the second parameter has the highest address, X is right below that, and then right before we continue execution from main into add, we have the return address back to main stored here. Now I really shouldn't say return address to main, it's just a return address back to the caller. So that's what the stack looks like, and the stack pointer points to the last thing that we push on the stack. So the stack pointer is pointing to the return address on the stack. X is technically 1 byte past, so the offset is 1, and then Y is 2 bytes past where the stack pointer points to, so it's really D plus 2. All right, so that's what the stack looks like, and this time I technically do not need to adjust the stack pointer to allocate for the local variables, but for those of you who just want a very consistent way that works for every single subroutine, you can always do this. Okay, you can always say LDI. Let's use register B, because register A specifies a return value, so we don't want to accidentally step on that. So we say add local var size, add this is subtract, sorry. So when we allocate, we subtract, which is kind of counterintuitive. So we allocate and then we deallocate down here. So let's do a YY, paste, add DB. So basically, even though add local var size is a 0, which means line 13 and 14 together doesn't do a single thing. Line 18 and 19 together does not do a single thing. it's okay, because if later on I choose to change my mind and start to use local variables, this code doesn't need to change anymore. I just have to change the label, add local var size, and I don't have to worry about a single thing because this part is already done. So what we need to do now is to access local parameter x and then parameter y, add those two together. So the format is pretty mundane, hopefully at this point. So we add AD because we don't want to change D. Okay, we want to change register A but not register D. So now A is the address of X. So we do LDAA. So register A now has the value of parameter X. Then we do the same thing with Y using register B. So now register B has the value of parameter Y, and then we just have to add those two. And we want to store the result into register A because register A is what is going to specify the return value of a subroutine of a function. So add AB is the correct order. So we deallocate the local variables if there's any, and then we can go back and retrieve the return address from the stack, deallocate the return address from the stack, and then continue execution at the caller. So this is the implementation of add, which is not the fun or the challenging part. The challenging part is in main. So the question is, how do we deal with that line in C, line 10 to be specific? So now the question is, what do we do with this? Okay, so we already know how to read parentheses, right? So when you have nested parentheses, when you want to perform the operation, you have to start from the innermost of the parentheses. So that means we have to deal with either this or this first. Okay, then we do the other one, and then finally we can perform the outermost add. So between these two, okay, add 37 and add 517, which one should we do first? Our intuition is going to say, well, since we read from left to right, let's do this one first. It's not like you cannot do it that way, but if you do it this way, it is very, very inconvenient, because when we want to perform this outer call, we want this to be pushed first. So that's why when we evaluate something like line 10, even though we instinctively want to read from left to right, but because of the way we push parameters on the stack, we want to evaluate these function calls, because they're all parameters, from left to right. So this is what we need to do first. Okay, so we get here. I'm looking at my time. Okay, so we are running out of time, so I will leave this program quote-unquote unfinished. For those of you who want to kind of move ahead, okay, after you get the lab done, if you want to, you can go ahead and try to complete this program, and then we can compare. You can compare your solution to my solution tomorrow. But I'm not going to make this one a graded assignment. So if you want to do it, go ahead. If you just say, okay, I think I'll be pretty good if I just get the lab done, that's perfectly okay as well. But we'll continue with tomorrow's lecture with this program, which is a nested call. And once again, you do not have a nested call with a swap subroutine. So what the new material that we are talking about in this particular program is really not that applicable to your swap subroutine. All right, so I think I'm going to conclude today's lecture. Unless somebody has a question that relates to the whole class, then I can address that question before I stop live streaming. So is there any question? All right. So if there are no questions, I'm going to turn off live streaming, and then what I'll do is I'm going to come back in 10 minutes, and then I'll start to answer some questions.